Hello, Ken.
Hello.
Hey.
Hey.
How are things going?
Things are going good. I have a lot to do this week, so
Half of it is this course, I suppose, right?
yeah, just like this and quantum and everything. Some research and stuff.
Remember that the midterm exam doesn't have to be due on the due date. Like, keep it flexible, okay?
Okay, cool. Yeah.
So keep the homeworks, one can stick to it, but I think midterm maybe anytime before the end of the exam, like in end of the semester, you can submit in. Okay, let's keep it like, because I noticed that I will be putting in more homeworks for this course, and it might really disturb when the midterm shows up in between. Because midterm acts like a homework, that's the thing.
Right. I should be able to catch up this weekend. That's my plan. So.
Okay. So talking about homework, I posted a new one, right? So, like, I'm aware that there's sufficient things pending, but this is what the plan is going to be. So there's going to be a homework 11 that's due April 8th on Thursday. And then there will be a 12, 13, 14 basically. So this will be due 15, 22nd, and 29th. That's the last week of classes. So so I'll keep going with the plan, but feel free to make yourself flexible with the dates. But eventually it will hit a wall, right? At the end of the semester, you have to do everything. So it's fixed amount of time. Does that seem reasonable? What do you think, Ken?
Yeah, no, I think that's perfect. Honestly, that's perfectly fine with me.
Okay, so we developed a whole formalism called the Lagrangian formalism or the Hamiltonian formalism to deal with problems that involve Newtonian physics, correct? And of course, the most important problem of all, which historically led to all this, is the planetary motion. Like it was possible to predict the motion of planets to great precision using Newtonian physics and using Newtonian law of Newton's law of gravitation. So we want to use this, study this problem, and we'll use Lagrangian physics basically as the background to do it, but it's pretty much independent of all of it. But in the beginning, we'll write the Lagrangian. So this is broadly called the Kepler problem. Why is it called the Kepler problem? Any idea? The motion of planets around, the study of motion of planets around the sun. is called the Kepler problem. And why is that? History. Any idea? Ken?
Not in particular, unfortunately. I'm sorry.
Yeah, that's okay. So the idea is, the history goes like, I think about 100 years before Newton, it was Tycho Brahe. He's from Italy. He was given a lot of funding from one of the kings to study all these planets. And he made a lot of detailed study, very precise measurements, and he had a lots of data, very good data there. But one has to analyze that, and it was Kepler whom Tycho Brahe appointed to analyze this data, and he could analyze all this data and conclude few things. These are called Kepler's laws of motion, and so maybe I can write that, right? So Kepler's, what are they called? Kepler's laws of, Kepler's laws, I think, for planetary motion, I suppose. He wrote a book, like he was a contemporary of Galileo. He was there before Newton. So the conclusions he made just based on data, Tycho Brahe had the data and he analyzed this data and he concluded the following: all planets followed elliptic paths. Until then, it was thought, or it was not. Nothing was said about it. It was expected that it will all be circular, but he showed that it was all elliptic based on his data. The second is that the amount of area the planets sweep. Oh, by the way, the first law also says that with sun on the focus, right? With sun on one of the focal points. And this is a little exaggerated view of the planets, but if you're talking about Neptune or so, this is how the orbit looks like. But if you're talking about Earth, how the difference between a circle and an ellipse is not very significant in the case of Earth. It is only about 1 or 2% off. That measure is called the eccentricity. We'll define this more precisely here. Eccentricity E. For eccentricity is a quantity that measures how much the ellipse is off from the circle. So if the eccentricity is 0, that means it's a perfect circle, and if eccentricity is 1, it is an extremely infinitely long ellipse. So if you have the sun sitting here and there is a planet going around and it sweeps, so in equal amount of time, if you were to say that, okay, in 1 month the planet goes from here to here, and in another month later in the year, in the same amount of time, it goes from there to there. And it turns out that the area it sweeps along the ellipse, so this shaded area that I've shown, in the same amount of time, the area is the same. So area swept is equal in equal amount of times. Today, we understand this as the statement of conservation of angular momentum. This is a consequence of conservation of angular momentum. And the third is the time period of any planet is proportional. Time period square of any planet. That's how do you say this? Time period square of any planet is proportional to the radius cube of the same planet. So this is proportionality. So that means that there's a constant, right? So this is equal to a constant times c times r cubed. Okay. Have you seen this before? Probably, right? Maybe not as Kepler's law, but somewhere.
No, I think I've seen it before. So
Yeah. So the history goes like these laws were there before Newton started his work, and Newton gave his law, Newton's law of gravitation, which could actually explain all these things starting from one equation. So Newton's law of gravitation is Newton's law of gravitation is that given any mass, there is a force acting between them, and that's equal to gm1 m2 over r square, right? Where g is a universal constant. It does not depend on the material, does not depend on which universe you're in, or we say which universe you're in, like we don't know what galaxies and other things are made up of, but the expectation is that this law is valid everywhere. In that sense, it's universal. And if r hat is the is the vector connecting the two masses, then the force is in the negative r hat direction. That means if you sit on one of the charges, it's either in the radially outward direction or radially inward direction. So it is attractive in that sense. That's Newton's law of gravitation. It has a potential energy associated with it. Remember, potential energies can be associated with a force only if it is path independent. That means to say there is no dissipation associated with it. And the potential energy is negative gradient of potential energy. So U is equal to negative G M1 M2 over R. Okay. And it was so successful, excuse me, this equation was so successful that to explain all the planetary motion that was going around, that everyone started working on it. And very soon, within, I think, within 50 years or so, Lagrangian had written a Lagrangian formalism. In another 100 years, there was Hamiltonian formalism, and this was every planet was worked out in detail, and you could do 2-3 planets simultaneously, but not too accurately, because for 2 bodies this works out great, but even with a single third body this becomes very untractable. It's very hard to track the equations if you have more than one equation. It can be done numerically to a certain extent, but there is a lot of information that is hard. It becomes very challenging when you have more than 2 masses. Okay. Okay, so that's what we want to deal with, and let's keep it very general at this point. Let's not say we have to Newtonian force acting between the 2 masses, but that's the context. So let's have 2 masses, M1 and M2, right? And so one is having position vector R1, the second one has position vector R2, right? So with respect to the center of mass of the 2 masses. And of course, the distance between them will be R2 minus R1. Usually, that distance plays an important role. And let's say the interaction energy between the 2. So remember, there is kinetic energy associated with M1 because M1 is moving around, M2 is moving around. But what is it that actually makes them move? What is the force that is making it move? We will say there is only one force for that purpose, and that's the force acting between the 2 objects. And of course, that's Newton's law of gravitation. That's what we have in mind. But for now, let us say that it could be any potential of the form R1 minus R2. But of course, we have in mind that this is going to be minus G M1 M2 over R1 minus R2. And notice it is the magnitude that shows up. So that means it is not just R1 minus R2, it is the magnitude of R1 minus R2. So it's more than what I have written it on the left side. For some time, I'll keep this general. I'll not start by saying that it is of this form. We'll start by saying any potential energy that depends on the difference between the two positions of the objects. That's what we want to consider. What will be the Lagrangian for this system? So L would depend on the position of the first mass. It will depend on the velocity of the first mass, which is the derivative of the position. It will depend on R2, the second position, and it will depend on velocity, which is V2. And if the potential energy depends on time, it can depend on time also, but we don't want to consider that situation. We just want to talk about two masses in this universe. That means we are talking about sun and a planet, just one planet. We are not considering more than one planet. It will turn out that it is pretty accurate, but not accurate enough to predict all the planetary motion or all the astronomical observations that we can do, but still sufficiently precise that we can tell that on this day or at this hour, the planet will be in this part of the sky. So this will be equal to, based on our, we have worked on sufficient number of problems now, and this will be half M1 V1 square plus half M2 V2 square plus minus the potential energy. So that's minus of U of R1 with R2.
Dr.
Okay.
Shajesh,
Yes, please, Ken.
I have a quick question. Yeah, why is it R1 minus R2 and not R2 minus R1?
Oh,
Or is it just because of the absolute? It doesn't matter.
Eventually, it is not going to matter. So, like, if you like R2 minus R1, I think I like R2 minus R1. How about that?
Okay, I was just curious. Thank you.
There's going to be complete symmetry between the two. But as of now, I haven't said that this is dependent on magnitude itself. So in that sense, there is a choice there. But if you think of it, I mean, in space, if there are just two particles, who cares what I call one or two? So just there must be some symmetry saying that this should be independent of this R1 and R2, correct?
I see. Yeah.
Yeah, just because how can it matter what I call them, right? Or what you can say is that this actually gets interesting later on. This can be a quiz problem, right? If you have just two masses in the universe, and that's the only two masses we are talking about, correct? And so there is M1 and M2, that's it. And you have physics associated with that. You like the Lagrangian, you get equations of motion, and that pretty much decides how the particles are going to move with respect to each other, correct? And then you can ask, what if I were to have another universe in which I swap the two particles, right? M1 and M2 are swapped, their positions are interchanged. Will the two universes be different in any way? Like, that means to say, by different, what I mean is that when you think of physics, right, there is a motion, there is a path of the particle. Is there any difference between the two descriptions that you have? Right? That's a question one can ask, and this is addressed, and this plays an important role. And this is what is pretty much called what's a boson and a fermion. Have you heard of these things?
Yeah. I'm not too familiar, but yes, I know what they are.
So what's a boson and what's a fermion? Maybe I can ask.
Yeah. So boson is a particle that has a spin one half, I believe. Right?
That's correct.
Of
Or either spin 1 or 0, like they are
one,
integer.
yeah.
The bosons have integer spins, so 0, 1, 2, and fermions have half integer spins, half 3 by 2. So
Right.
it turns out that most of the particles that have mass in our universe, they are fermions. And most of the particles that do not have a mass turns out to be bosons. Okay. There could be of things in there. For example, photon is a boson of spin 1, electron is fermion of spin half, but then you have Higgs particle that has been detected recently that has a spin 0. So that kind of takes away the pattern in that, but that was not a very fundamental pattern, it was just an observation. But that is, of course, that's correct definition, but the interesting feature about fermions and boson is that they have a different statistics. That means to say that if you have two bosons and if you were to swap them, correct? So you have a box of bosons, think of a lot of billiard balls, and each of the ball is a boson, correct? And you have a lot of white colored billiard balls. Each of them behaves like a boson. And now I interchange one of them. Like I pick two of them, then interchange and keep it back in there. And the question is it any different from what you had earlier? And the point is no, boson doesn't care for the swapping of the two particles. But fermions care. If you were to swap two fermions, two electrons, for example, they care. The energy gets different. Okay.
Okay, that's interesting.
Yeah, that's interesting. And the statistics gets very different because of that. And there is a whole, I mean, most of the, for condensed matter physics depends on the statistics significantly. Okay, so this is what is basically broadly called Pauli exclusion principle. Have you heard of Pauli exclusion principle?
Yes, I believe so, where only a electron can occupy one space.
Exactly. So that is basically explained in terms of this. This is what it is that, okay, fermions don't like to be swapped, and then the energy is different, and so on. So let's have a quiz to be, just to introduce you to this. So what's the difference between boson and fermion statistics? Okay. Just a uh, just general knowledge. So it's an important concept. In somewhere in thermodynamics or statistical mechanics course, you will see. Okay. And yeah, and your question actually relates to that somehow, because you're
Okay.
sort of slapping them, right? And it is a good question at some level, but here I think it is, for me, it was just a matter of notation. And later on, I'm going to make it magnitude anyway, so why should I bother? Okay.
Right. Okay, thank you.
Okay, so that's our Lagrangian, and that seems like that's a lot of variables, like three coordinates for mass m1, three coordinates for mass m2. That's like 6 variables, already a lot of work. And actually in this context, I like to say that typically if you're doing fundamental physics, that means you're analyzing something from the scratch and you really want a lot of predictability power. Typically 3 variables are hard enough. Like 2 variables are easy to analyze, like you can make a plot and get it. If there are 3 variables, it gets hard, but still tractable, very tractable. And if you have 4, it's harder, but still doable. Most of the times, by the time you reach 6 or 7 parameter, you have to be really clever to be able to see what's going on in the physics. Like if you have a model that depends on 7 parameters, that's extremely hard to analyze already, even with all the all the computers and all, because you have to know what you're looking for. So, right, I mean, computers help you, but 7 gets hard. But that doesn't mean that there are no models that are not having more than 7 parameters. Classic examples are standard model, the particle physics that describes most of what we see as forces around us. And that has about 20 to 25 parameters. Most of them are masses, like how many particles they exist. But more realistic model, like that you see on an everyday basis, is the weather model. Weather model has about 17 parameters based on, basically they are like you make a big computer algorithm, and the input typically is what is the weather, what is the temperature and pressure and humidity in, let us say, at this place on Earth, it could be Madagascar, right? What is the temperature, pressure, and humidity there? And similarly, they pick some parameters here and there, and that pretty much decides what's going to be the weather in the future, right? Let's say 3 days from today. And typically the predictability is only of that level. I mean, my maximum 1 month and all that, with a lot of error in them. So that tells you about the number of parameters. So here we have about 6 parameters, right? 3 parameters for the position of M1 and 3 for M2. And of course, you have to give the initial velocities also, and then the equations will predict it for you. So that's a lot, but actually, the system doesn't have that many parameters. This is just because we are starting from a very broad formalism. So it seems like it has 6 parameters. It doesn't have 6 parameters, and we will see how it is. First thing is that this motion happens in a plane, then angular momentum is conserved, energy is conserved. So when you use all those relations for you, then this collapses very quickly. Okay, so how do we start? So let's say, of course, we can directly at this stage, if you want, we can write down our equations of motion, correct, using Euler-Lagrange equations, but we will be clever about this. Let us choose a coordinate system. Let's choose our a frame in the following way. We know that there is a center of mass. Definition of a center of mass, remember, is center of mass is a position. So this is our center of mass. So that's equal to M1 times the position of R1 plus M2 times position of R2. And you have to divide by mass M1 over M2, right? That's the center of mass. Center of mass, of course, is a point in space. If the 2 masses are reasonably equal, then it's somewhere in the center. But if it is not equal, if one outweighs the other significantly, then it will be significantly closer to the other. Example is Earth and Moon. That's a 2-body system, and you can ask where the center of mass is. Earth is significantly heavier than Moon, about 100 times heavier than Moon. That means that the center of mass will be very close to Earth. In fact, the center of mass of Earth-Moon system is inside Earth. It is inside the radius of Earth. Similarly, one can ask, if you talk about center of mass of our planets, like Jupiter is there are all these planetary objects, and there is Sun. Sun is huge, right? Sun is about 1 million times larger than Earth, and the biggest planet in the planetary system is Jupiter, which is still 1,000 times smaller than the mass of Earth. So one can ask, with all the planets spread out in the solar system, is the center of mass of the solar system really close to Sun, or is it inside Sun, or is it outside Sun? Right? So maybe that can be left as a quiz, right? So find out, right? I expect it to be inside Sun, but check it out. So is the center of mass of solar system inside sun or outside? Is the question clear? By inside, outside, I mean the inside of the radius. So you need a radius of the sun.
Right, right.
So just, I expect it to be inside, but look it up. Okay.
Well,
Okay. Yes, please.
wouldn't it depend on like which planet?
No, of the whole solar system, I mean.
Oh, okay, I see.
Whole solar system, including all the remote, what do you call them? The Oort clouds, right? There is an Oort cloud that is outside all the outside planet Neptune. Include all of them. Many of them go to zero because they are all spherically symmetric, but at least planets are not spherically symmetric. Let us say you can make it an even simpler problem. Let us say you keep sun on one end, put all the planets on a straight line, right?
Oh, I see. Yes.
Then ask what is the center of mass. That itself is an interesting point, but I think sun beats it significantly. But also remember that they are really far away, so distance also matters.
Right.
So in my, if I'm not wrong, it will still be inside the radius of the sun. Simply because it's so huge. Like Jupiter is the next planet, next in mass, and is 1,000 times smaller. But maybe if the distance is large enough, it can still beat it. So check it out. Yeah, I'll be curious. If it comes out outside the sun when you put them in a straight line, let me know.
Will do.
If you do the exercise, I mean, it's, don't spend too much time. Like all these things can take away a lot of time. But yeah, if you get interested, you should. Yeah. But don't spend important time on this. Okay, let me write this statement as M1 plus M2 times R. And so that's just so that because I'm going to introduce more coordinates. So there are two coordinates, R1 and R2, and I want to rewrite them in terms of the center of mass. I need one more, and the other coordinate is clear what it should be because I'm defining R2 minus R1, right? So let me write a small vector R as R2 minus R1. So R2 minus R1. So I want to rewrite my Lagrangian instead of R1 and R2. I want to write it in terms of capital R, which is the center of mass, and small r. So I want to invert this whole equation, right? So that can be done. Basically, what I will do is if I multiply the second equation with M2 and then add them, R2 goes away, right? Then I can get an equation for R1. So so I'm just going to do that in my head. So R1 will be, I'm going to multiply M2 and then add them, right? So these two cancel out. M2 makes it M1 plus M2. So this is equal to R plus M2 divided by M1 plus M2 times R. Okay. And similarly, R2 would be equal to, this time I have to multiply by M2 and then subtract no, I will multiply by M1 and then subtract. So this is so R2 is when I'm subtracting. So it is capital R minus M1 over M1 plus M2 times position. That's your inverse of that transformer. So I substituted these two quantities. So R1 and R2 will be that. And then I want to replace all the V1, V2s and all using that equations, correct? With me till now? Any questions
Yes.
there?
No questions.
Okay, so let's calculate V1, which is dr by dt. So V1 is dr1 by dt. Velocity is equal to dr by dt plus m2 over m1 plus m2 small dr by dt. Let me introduce some variables here. Let me call capital V to be equal to velocity of the center of mass, and small v to be the velocity associated with the relative position of the two objects. So then I can write this to be capital V, and this is small v. And V2 similarly is derivative with position R2, that's equal to minus M1 over M1 plus M2 times velocity. Using this, let's rewrite our Lagrangian. Okay. So let me change the board space. Okay. So our Lagrangian L, this time I'm going to write it in terms of capital R, the velocity associated with the center of mass, the relative position R, and the velocity associated with the relative position. Be careful with the V's. This is capital V and that's small v. That's equal to half M1. I had to substitute V1 with the relation that we had. So that's capital V vector, not capital V actually, V1, sorry, yeah, plus M2 over M1 plus M2, and that's small v square. And the other one is second kinetic energy is M2 small v minus M1 over M1 plus M2 square, and we have potential energy. It was R2 minus R1, so let's just, so that just depends on small r, right? Agreed? That of course simplifies immediately because I can add the individual quantities. So the first one is simply half M1 plus M2 times the kinetic energy of, this is the kinetic energy of the total system, right? M1 plus M2, if you want. There is of course a cross term which actually does it cancel out. So there is M2, 2 M2, and there is 2 M1, right? But then there is an outside, there is an M1 and outside M2. So the cross term which comes in opposite signs, they cancel out. Okay, and the other terms are plus. Let me do that. So separately here and then provide it in there. So that's m1 times m2 squared over m1 plus m2 squared, v squared, and then there is plus half m2 times m1 squared over m1 plus m2 squared v squared, right? That's the squared quantity associated with the relative velocity between the two masses. And I want to put this all together, so that's equal to half, that is m1, m2 common, m1 plus m2 common, and that is v squared, and whatever is remaining is, after I pull out m1, m2, there is m2 remaining there and m1 remaining there. So there's m2 plus m1. That cancels one of the relations, and what we have is 1 by 2 m1 m2 over m1 plus m2 times v squared. That is a nice way of seeing this. What is that product of two masses over sum of two masses? Notice that if I were to define a quantity, 1 over mu, remember your parallel resistors or series capacitors. So this is M1 or M2. And in mathematics, this is called, I think, the harmonic mean. So if you were to do this, what is this equal to? So that's M1 plus M2 divided by M1 times M2, which means that mu is equal to M1 M2 over M1 plus M2. Okay. This mu will be called the reduced mass. Because in this way of adding, mu is always less than the smaller of the two masses. Okay, it is like saying when you add two masses, the total mass is always larger than the sum, larger than the larger of the two masses, right? 1 over mu will be smaller than the smaller of the two masses. Okay, so with that, we know that this is half mu. Our Lagrangian then has this simple structure that it is equal to half mu reduced mass times velocity v squared. And the potential energy, which is U of R. So what have we learned here in this step is that the Lagrangian, even though we expected it to depend on 4 quantities, does it depend on the 4 vectors? Like remember, there are 4 vectors, so 4 into 3, 12 parameters, right? Does it depend on the center of mass position? Yes, it does depend on, but what it doesn't depend on is the velocity. Sorry, it doesn't depend on the position of the center of mass. It does depend on the velocity. So it does not depend on this. Right? I got rid of the 3 coordinates by transforming to this, right? That's usually the advantage of going into the center of mass frame. Okay, clear?
Yes. Yes, thank you.
Okay, so that's one simplification in a Kepler two-body problem, but there is an immediate simplification that follows, and that is that so what we are talking about is that there is M1 here, there is M2 here, and if you use these coordinates, then there is it does not depend on the position of the center of mass. That's like saying that it doesn't depend on the origin, right? But what we can do actually is we can go and actually sit on the center of mass. So this is actually, so this was your center of mass, all right? Typically it's somewhere in between along the line joining them. So that's your origin, correct? But now suppose you were sitting on the center of mass. That means to say center of mass moves as in a general reference frame, the center of mass moves. But if you were sitting on the center of mass, your velocity is 0, right? So that's called the center of mass frame. Go to the center of mass frame. So find the center of mass and then go and sit on that point, in the sense that if it is moving, you move with it. Right? So the motion relative to that point will be 0 as far as you're concerned. In that particular frame, this velocity v is 0. So v then is equal to 0. So in that particular frame. And in the two-body system, that's perfectly fine. Anyway, this has no interaction. Interaction energy does not depend on v. That's just showing up as a energy forever, right? This is not going to change. If you had to write the Euler-Lagrange equation for this, dv by dt is not going to have any effect from these two, right? So there is no force associated, a force on that particular term. So it is a constant. So go and sit on that point, and you're taking away. So remember that, recall that Euler-Lagrange equation will have dv by dt will be equal to 0. Is that clear what I mean there? Like I've not explicitly shown it.
Yeah, I understand.
Since that is equal to 0, so v is equal to a constant, so I can go and sit in that frame. That's an inertial frame. So that's perfectly fine. So v equal to 0. And the moment you write that, that is significant simplicity. Now in that center of mass frame, the Lagrangian is dependent only on the relative position now of the two masses and the velocity associated with those two, with that relative position vector. And the Lagrangian is half reduced mass velocity square minus the potential energy, which depends only on the relative position of the two masses. Oops, I'm not in the screen. Okay. So from 6 or 4 vectors, we have come down to 2 vectors, which is basically 6 components there. So already significant progress. Correct. Okay, so that's good. Next, let us say that let's define what is called a central force. So that takes you back to the question you asked, why was it R2 minus R1 and not R1 or R2? And I said it's only the magnitude of it, it casts off in the Newtonian gravity. So let's define what is called a central force. A central force is a force associated with the potential energy when the potential energy depends only on the magnitude. So U is dependent only on the magnitude of R. That's what is a central force. But more formally, what it means is that the cross product, so R crossed with the force, so central force, right? R crossed with the force is equal to 0, right? That means to say if the force is always radial, right? Central force means it is always pointing in the radial direction. So force is having a radial component only all the time. So that means R cross F is 0, correct? That's the starting point of a central force. Okay. If R cross F is 0 and F has a potential energy associated with it, so that's R crossed with gradient of a potential energy is equal to 0. Correct? And it should be a negative sign there because F is negative gradient of the potential energy. Gradient in spherical coordinates reads r hat times d by dr plus theta hat times d by 1 over r d by dr, sorry, d by d theta plus phi hat 1 over r sine theta times d by d phi. Is that familiar?
Yes. Yes. Why is it negative R though? I missed that. I'm sorry.
Oh, because force and potential energy by definition are connected by force is negative gradient.
Oh, I see. Thank you.
But since it is zero, it doesn't really matter. So since r cross r is anyway zero, so the first one doesn't contribute. And what we have is r cross theta. So let me go to the other board. So I have r crossed. So r cross r du by dr plus r cross theta 1 over r du by d theta plus r cross phi 1 over r sine theta. Potential energy with respect to phi is equal to 0. This anyway is 0. That's gone. If this has to be 0, there are two equations necessary. You have to have the derivative of the energy with respect to angle theta is 0, and the derivative of the energy, partial derivative of the energy with respect to angle phi has to be 0. That means that it has to be completely angle independent. Correct? So that means to say that u of r in spherical coordinates will be u of r theta phi. So it cannot have any theta dependence. It cannot have any phi dependence if it is a central force. And that's what you typically say. So a central force requires that energy is dependent only on the magnitude of it. Okay, so that's the idea of it. Central force. Okay. So what we have is a Lagrangian which is dependent on vector r, velocity v, and we said it is given in terms of a reduced mass, velocity square, minus the potential energy. Now we confine ourselves to central forces. Kepler problem involves a central force. In fact, this will be Gm1, M2 over R, right? That's what we will do. But this is applicable for any central force. That's the idea. It doesn't have to be 1 over R squared. It could be 1 over R cubed, and so on. Any central force, this formalism will work. Let's go ahead and see what our Euler-Lagrange equations are. So you would say, first get the canonical momentum, right? So this is canonical momentum. That's V is equal to mu times velocity V. And that's it. There is no velocity dependence in this. Oh, I had to move my camera.
Yeah, sorry.
Sorry for that. Okay. With me? So I said the Lagrangian is this. And earlier I had written it as vector r here. Now I'm confining myself to central forces. That means this is magnitude of r. Okay. So canonical momentum is this, and the potential energy, right? Gradient d by dr of L is equal to minus gradient of u. So our equations of motion is the Euler-Lagrange equation is derivative of this is equal to that, right? So the d by dt of the canonical momentum is equal to negative gradient of L, sorry, gradient of L, right? So this implies that mu times dv by dt, right? This is also P, right? Canonical momentum. So I can write this to be dp by dt. P is m times mu times v. So dp by dt is equal to negative gradient of u. Okay. Let's see what happens to angular momentum at this point. So angular momentum, remember, is defined as angular momentum is R crossed with P. Right? The momentum P. Then I can immediately ask, how does the angular momentum change for the system with time? There are two pieces, R and P, so I would say this is dr by dt crossed with P plus R times R crossed with dp by dt. dr by dt is velocity, P is velocity, P has velocity in it, so this is 0. And the second quantity, dp by dt, is negative gradient, so that's R crossed with gradient of potential energy. But that's the definition of the central force, correct? That this is 0, which is 0. That's exactly equal to 0. That means that angular momentum is constant. So in Kepler problem, if the forces are central, or for that matter, any two bodies problem where the forces are central forces, angular momentum is conserved. Further, let us see what is R dotted with L. Angular momentum is conserved, so angular momentum is constant. So there is a vector for the whole system. For when a planet is going around the sun, there is one vector which does not change its orientation at all. If it is pointing to a star, it will keep pointing to a star all through the motion as the motion is going around. So let's see, so that has special meaning there. So let's see what is R dotted with L. So the position of R dotted with L, so that's R dotted with R cross P. That's immediately 0 because R cross P is always perpendicular to R, and R dotted with, that's always 0. That means that wherever the planet is, the relative position of the two planets will always be perpendicular to the angular momentum. It is intuitively clear that if you're having two masses going around, they will be going around in circles probably. So this is, and their position will always be in a plane, right? So that's how we intuitively see this. And the angular momentum, if you think of this as a circle, that's always perpendicular to that plane, so that's L. But that's not obvious from a very, is it always the case that you might worry about it? With a little thought, it comes out very easily. But we have proved it in general that for any two-body system, if the forces are central, an angular momentum is first of all conserved, and the motion happens in a plane perpendicular to the angular momentum vector. So there is a constant vector that doesn't change, and there is a plane. So the motion happens in the plane, in a plane perpendicular to L. Any questions on that? Ken?
No,
Okay.
no. Maybe
So-
later.
Yeah, sure. R, which can be in spherical coordinates written in terms of R, theta, and phi, right? That's your position vector R. So it happens in a plane, so I don't need 3 coordinates to describe that. So I will choose theta to be equal to pi by 2. So theta equal to pi by 2 is a plane, right? So I pick that, so it's a choice. Since I know that it's going to happen in a plane, I choose my angular momentum to be perpendicular to that motion. It all depends on the initial conditions. Like if you shoot the planet in the initial direction in a certain direction, then that decides the plane, right? So there is no theta there. Okay. So if that is the case, then my Lagrangian simplifies significantly. I want to work only in the polar coordinates R and angle phi. And of course, there will be a velocity related to R dot. And there will be a velocity related to angle, that's phi dot. So that's all that we need. If that is the case, then my kinetic energy simplifies half mu R dot square, and the angular part gives you half mu R square phi dot square, which we have seen in different problems, right? And potential energy still is only a function of R. Is that clear how I wrote this?
Yes.
Did I write on that?
No, I understand.
Okay. So that's your Lagrangian, and we immediately want to write our equations of motion. So let's rewrite our equations of motions for this Lagrangian. So L, we rewrite that phi dot is equal to 1 by 2 mu r square plus 1 by 2 mu r square phi dot square minus u of r. What's the momentum associated with the variable r? That's simply equal to r dot square. So this is r dot now, right? Momentum associated with r. So let me call that P of r, let's say. So that's just this term. So that's mu times r dot. There is also a momentum associated with the angle phi dot. That's actually what we call as the angular momentum. So let's call that L. And since angular momentum is now already chosen to be in a certain direction, let's choose that to be our z-axis. So that's Lz, the z component of the angular momentum. But there is only z component. There is no other angular momentum. Oops, I think I'm slightly off. Okay. And what is that equal to? Phi dot, that's mu r square phi dot. That's your angular momentum, and that's your radial momentum, if you want, or momentum associated with the radial coordinate. Euler-Lagrange equation also requires us to calculate the change in the Lagrangian with respect to r, and what is the change in the Lagrangian with respect to angle phi, right? That's a generalized force, if you want. The generalized force with respect to r is there are two pieces. One can come from here, or the second would come from here. So when it comes from here, it is mu r phi dot square. Again, there are two of them, so the factor 2 goes away. And this one is simply a partial derivative of u with respect to r. Since we don't know that, we have kept it very general. Any potential energy in the Newtonian gravity, it will be 1 over r. So that will be 1 over r square if you want. What about the change in the Lagrangian with respect to derivative of phi? There is no phi dependence in there, so that's 0. And that's again a statement that there is no torque acting on it, right? Generalized force associated with an angle is called a torque. That's no torque. So let's restate that statement. As far as the radial coordinate goes, the total derivative of this, so d by dt of dot has to be equal to dr, and d by dt of dl by d phi dot is equal to partial derivative of L with respect to phi. This implies that d by dt of this, which is mu r double dot, right? So second derivative of r is equal to whatever we have on the right side. So that's mu r phi dot square minus du by dr. And the second equation associated with the angular motion is equal to the statement that so there is d by dt of mu r square phi dot is equal to 0. Okay, which immediately implies that this is a constant. This is mu r square phi dot is a constant, which we will call Lz, right? And let's stop calling it Lz. Let's make it lift into total angular momentum. There is only one. All the angular momentum is in the z direction. That's what it is. Let's choose that to be L. Any questions at this stage, Ken?
No questions. Thank you.
Let's spend a few minutes asking for what is the implication of this angular momentum being conserved here, this equation. So let me read that as, so there is mu r square d phi by dt is equal to L, which can be written as mu r square d phi is equal to L dt. Now what does that mean? Notice that dt is always greater than 0. So dt is always greater than 0 for a particle, in the sense that you only go into the future, right? You never go into the past. Correct? And that implies, since we have L, which is having a fixed value, r square is a fixed value, that means d phi, this implies that d phi is monotonic. If dt is greater than 0 and r square anyway is greater, and if L is also greater than 0, then d phi is also greater than 0. There's a chance that you will choose your coordinate system in such a way that L is negative. Then you would say that, okay, if L is negative, then d phi is negative. But it's, once you choose it to be negative, it will always be negative. Which means that phi can be used as a measure of time. Right? Which which is what we do, right? When we say that we are 30 years old or 50-year-old, what do we mean to say is that we have gone around the sun 50 times, or we have gone around the sun 10 times, 12 times, 32 times, right? That's a measure of time. That's angle, right? That's because of angular momentum conservation. If the angular momentum was not conserved, you couldn't have used the number of times you have gone around Earth as a measure of time. A simple conclusion, but a consequence of angular momentum conservation in the planetary motion. Right? That's one thing. And is there a second conclusion I wanted to make in there? I was thinking, let me see, something in mind. Oh yeah, that's Kepler's law. So let's think of like Kepler says that the area swept is the same, right? And I made a comment that it is a statement of conservation of angular momentum. So let's think of an elliptic orbit, or for that matter, it doesn't have to be elliptic, any orbit, right? So let me clarify that. So if it is any, so this is part of any curve, I don't know which curve it is, like it is expected to be elliptic if we believe Kepler. And between 2 points, let's say this is angle d phi. Right? That's the change that happens between 2 points. It goes from point 1 to point 2, and the angle that spans is d phi. What's the area of that infinitely thin arc length, if you want, or the area projected on the center due to the arc length? This will be equal, so area would be equal to half times the length of this, that's r, times the base, which will be the arc length, which is r d phi. Base times altitude, that's the area of the triangle. I'm saying that this is really infinitely small. When it is infinitely small, that's pretty much a perfect triangle with its base pretty much straight line. And its area is half r square d phi, which is the same, right? R square d phi shows up. So area per unit time, right, area over dt, let's say, is equal to half r square d phi by dt. But r square d phi by dt is nothing but L over mu, which is a constant. So if angular momentum is constant, then the area swept by the particle, or the relative position, if you are sitting on one of the masses, then the area swept by the other particle relative to you will remain the same with respect to time, right? So that's one consequence of it's two consequences of the angular momentum conservation. And of course, the third relation is that, or the important point is that once I have that relation, I can use that in the second equation so I can use this to substitute phi dot inside in here. And I replace phi dot with L over mu r square. So I can get my equations completely in terms of r. So let me do that. So I go back to this. My equation is mu r double dot is equal to mu r, but instead of phi dot, I write L over mu r squared. And then squared because it is phi dot square, and minus mu by dr. That's nice because that's one differential equation in r, and that's it. That describes my motion completely. From all the way back in 12 parameters that we had earlier, now we are down to just one radial parameter, and that describes the planetary motion completely. So very simple in that sense, but let's we have to still solve it, right? So shall I take a few more minutes, Ken? Are you free?
Yes, yes, I'm free. No rush.
So that's our equation. Let me process this a little bit. So this is mu or double dot is equal to process this actually. So this is mu r L square mu square r raised to 4, right? Yeah, I think so. Right. One of the mu cancels out, one of the r cancels out. So let me do that. And this is mu r cube is equal to minus du by dr. Okay. So from this point, so that's a differential equation we have to solve. Still notice that we have kept this very general. U is any central force. So the trick to solve this equation is to multiply by r dot. So multiply this whole equation by r dot, and then we can identify the quantity that comes out afterwards. Okay. So let's see what this is. R dot times r double dot can be written as total time derivative of half mu r dot square. That's the left hand side, because when I take the total time derivative, it can get two r's. One is r dot times one is r double dot, right? That's your r dot and r double dot. Right? So that's one relation. Here you get a r dot and an r cube. For that, what I do is that I realize that, oh, if I time derivative of 1 over r cube is nothing, so 1 over r square actually, 1 over r square is equal to minus 1 over r cube times r dot. Right, this chain rule. So maybe use that relation in that. So there is an r dot when I multiply, then is an r cube, so there's a negative. So this is total time derivative of minus L square over mu r square. So if I take the time derivative of this, I get that. And again, r dot, also notice that d by dt of u, right? Just the energy u. I'll use a chain rule again. This gives you, so this is the same as, let me write it here, du by dt is equal to dr by dt and partial derivative of u with r, right? Again, a chain rule relation then. So that's the same as minus u. That's it. So that's a total derivative term. So that lets us know that, oh, that's a constant of motion. If I identify this properly, there seems to be something that remains constant. So this seems to suggest that d by dt of half mu r dot square. Put it on the left hand side. That's L square over mu r square, and plus u is equal to 0. If total derivative of something is 0, that means that must be constant, and that is indeed the energy. In fact, it is the Hamiltonian. If you start with the Lagrangian and do this PV minus L, that comes out to be the Hamiltonian, which is the energy. So we will call this E. So this constant, we will call it the energy, L square over mu r square plus u will be your total energy. That's constant. Okay. Let me process this a little bit more so that we get the equation, and then I'll stop there. I won't solve the equation. Okay. So let's go back to this, get some space. Okay, so we have 1/2 mu r dot square, right? R plus L square over mu r square plus U is equal to energy E. Let me rewrite this so that I can put this on the other side. So this is dr by dt whole square. That's your r dot square. Rest everything, I'll put it on the right side. So that's E minus U. But then I had to actually get this 2 over mu there. So it is 2 divided by mu, multiply by 2 divided by mu. And then there is minus of L square over divide by mu, so that's mu square r square. And I multiplied by 2, so that's a 2. Was there a 2 there? Yeah, I think that's 2. Let me check. It seems weird. Oh, did I mess up? I did mess up. I did mess up. Okay. Let's go back a little. Are you there, Ken?
Yes.
Notice that when I did this, I made an error. Right? I wanted to recognize that the time derivative of 1 over r square is r dot over r cube, correct?
Right.
But the derivative of 1 over r square is minus 2 over r cube.
Oh.
It's the 2 there.
Yeah, I see.
There is a factor of 2 here, right? I introduce that 2 there. Where will that 2 go? That 2 will go in, right? So I have to replace this 1 over r cube with that. So 2 will go in the denominator. So if this is equivalent to saying this is 1 over 2. So that's where I have the 2 there. Okay, with me?
Yeah.
But if there is a 2 there, there will be a 2 here. And I circle that so that you know where to look for. Okay. That 2 will go in here. 2, circle it so that you know what I've added. That 2 shows up here. Circle. And that 2 shows up as the next step here. So energy has this factor of 2. Is that clear? Did I confuse?
No, that is very clear. Thank you.
If that's the case, then this here has a factor of 2, right? And then I don't get this extra factor of 2. This is okay. Yeah, that's what I remember. Okay. So my equation is velocity, if you want, dr by dt, radial velocity is equal to square root of E minus U 2 over mu minus L square over mu square times R square. Let me, since you're allowing me the time, let me do one more step, because otherwise I'll have to do more work to get it back in. Like just one more step. Remember that angular momentum is conserved So we have mu r square times d phi is equal to L dt, right? So I can use that to replace this dt with d phi. So let me replace dt with d phi. Remember, time and angle are the same, right? I can use either one to write that. So dr will be equal to, instead of dt, I will say it is mu r square over dl. Right? So yeah, so this is mu r square over L times d phi times that. Since everything is r dependent, usually this is written on the opposite side, right? Because if you want to integrate this, there is r dependence is all here, so you will keep d phi on one side, and dr is kept on the other side. So this is dr. So this will be L over mu r square, and this becomes 1 over e minus u 2 over mu minus L square over mu square r square. Let me take the mu inside, just one more step, and after that we'll solve the equation later. So this will be L over r square dr, and mu I can take it inside, so this will be so once I multiply the mu in there, that is 2 mu inside the square root becomes mu square. This is 2 mu square times e minus u, where u has to be made more precise, minus L square over r square. And that allows us to do something with dr over r. So basically we will be able to solve this. Solve this simple.
Shouldn't it be mu L squared over? Oh, you didn't square the. I see. Sorry, my bad.
Oh, no. I think you're correct.
No, you just didn't. I don't know if it's squared right there. The L squared over mu r squared. I think it should be
Yeah,
L
so
squared
this
over mu squared.
right? That's what you're saying.
No, above that.
Oh, this one is mu
Yes.
square.
Yes, that's. I just didn't see that. My bad.
That one, and this one also, this should be mu, I suppose. Yeah, that's correct. Yeah, that's correct.
Yeah.
Very good. Yeah, thank you. Okay. So that's how we could. So 2 times mu times change in energy with respect to the potential energy, and minus L square. And this will be solvable, and we will see that this leads to the solution of an ellipse. In fact, it is not just an ellipse, it will be a conic section. It can be an ellipse, it can be a parabola, it can be a circle, it can be a hyperbola. Any of those equations are possible, planetary motions possible. And we will investigate that next time to good extent. Okay.
Okay, great. Thank you.
Okay, thank you for allowing me the extra time. It helps a lot.
Oh yeah, of course. Thank you.
Okay, see you. Enjoy.
Oh yeah, good. Have a good day. Goodbye.
Bye.